Okay, just as a start, so for forces and pressure, there's quite a fair bit of things that we need to cover. However, most of it you have actually covered in Sec 2 quite in depth for quite a long period of at least for over quite a period of time. So I think it's really just a quick revision for this one. But I'm going to use a textbook to sort of like to run through the ideas within this chapter. Okay, so let's start now. Okay, so forces and pressure. Let's straight go to the first one. So in 3.1, we're going to learn what forces are. So forces are either a push or a pull, okay, in which an object can exert on another. Okay, so what are the two types of forces that we can see, that we can classify them into? One is called the contact force. The other one is the non-contact force. Okay, so these are the two types of forces that we can classify them as. Right? All forces can be classified into contact forces or non-contact forces. So what are the contact forces that we have? So first one is the normal reaction force. So this is a push exerted by a surface on an object pressing on it. Do take note, I want you to look at this sentence over here. This push is always perpendicular to the surface. So normal reaction force, normal reaction force, okay, the force exerted is always perpendicular to the surface. So for example, we look at this cup. The surface is over here. You look at the normal reaction force is over here. Maybe I should change a different color. We use blue. Okay, so this is the surface. This is the normal reaction force. What you realize is that, can you see, it's perpendicular to the surface. So normal reaction force is a force that's always perpendicular to the surface. Next one, another contact force is friction. Just note that friction always opposes motion. Okay, so for example, if I got a box that's moving forward, so there's a forward force. Okay, friction will always be acting along the surface. So this is the surface, is a box, right? So friction is a contact force. So at the point of contact, which is over here, it will oppose the motion. So this is the friction force. Okay, it's always along the surface. How you draw it, where you draw it, will make a difference. And the last one, another contact force that is being identified here is actually tension. So typically, it's always a rope or a string that you will find that there is this idea of tension over there. Okay, so those are the three contact forces. The three non-contact forces that you're going to learn in your in the whole of your physics is actually gravitational force, which you find in chapter 4. Electric force under static electricity, which is about, I don't know, is chapter 14. Last one, magnetic force, is chapter 18. So these are the three non-contact force that you will pick up along the way. So I won't go through in depth for all of this because along the way the chapters we're going to cover them. Okay, but regarding these three contact forces that you have here, normal reaction, friction, and tension, okay, you will realize that you will see it more in this chapter itself. Okay, so these are so just a recap. So forces is a push or pull. What are the types of forces that you have? Contact, non-contact. So what are the three contact forces that are listed here? Normal reaction, friction, tension. Non-contact forces, gravitational force, electric force, and magnetic force. We're going to cover this, chapter 4, chapter 14, and chapter 18. So that's for the first part here. Okay, we identified what the forces are, okay, how you can classify them. Now, when you go into 3.2, straight away you go into this concept of vector diagrams. Okay, why do we go into vector diagram? Because forces is a vector quantity. Okay, forces is a vector quantity. And remember in chapter 1 we mentioned, so what is our chapter 2 we mentioned what are vectors? Vectors are physical quantities, okay, that have both what? Magnitude and direction. Okay, so vector quantities are physical quantities that have both magnitude and direction. As such, because of the concept of you have direction in a vector quantity, you can't just anyhow add them up. So that's why we're going to learn a little bit more about the vector diagram, which is going to help us to learn how to add two vectors using a graphical method. Okay, so do take note how we can choose to draw a vector diagram. Okay, so let's just start with a simple example. Okay, let's just start with a simple example here. So I have a force. Okay, so I want to draw a 20 Newton force in the direction of 45 degrees. So what I'm going to do, measure 45 degrees, then I draw my 20 Newton force. So why is it 4 cm? Because the scale is 1 cm to 5 Newton. I can say it all like that because I understand what's going on. But in actual fact, there are a few steps you need to follow. First one, before you even start drawing, you need to choose an appropriate scale. So 20 Newton, in this case here, they have chosen 1 cm equals to 5 Newton. So I want to draw 20 Newton and the scale is 1 cm to 5 Newton. Therefore, I know that my 20 Newton will become 4 cm long. Okay? Next one, because it's 45 degrees north of east, I just take it as east is this direction. I'm going to measure 45 degrees towards the north. So that's why you draw a baseline and then you measure 45 degrees towards the north. Then after that, from this particular point here, you draw a 4 cm line. Okay? This will represent my 20 Newton, that is 45 degrees north of east. Okay? So this is the starting part of how you draw a force, okay, as a vector itself. Now, all you're going to do is once you have drawn a vector, learn how to draw a vector like this, we're going to learn how to add up the vectors. Okay, we're going to learn how to add up the vectors. So I'm just going to skip all this. Okay, we're just going to go straight into this. Now, when you're adding vectors, okay, maybe let's just change the word. Okay, instead of using the word vectors, let's use the word forces, since forces are vectors anyway. So if I want to add parallel forces, right? If I want to add parallel forces, so let's look at the first example. 3 Newton, 5 Newton, they are parallel. Both are acting towards the right. If they are parallel forces, both are acting towards the right, you can just add them up. The resultant force is 8. Alright, resultant force is 8. If I got 3 and 5, can you see they are still parallel forces? It's just that they are acting in different direction. Okay, parallel but in opposite direction. Because opposite direction, you can subtract them off. So 5 Newton to the right, 3 Newton to the left. Therefore, my resultant is 2 Newton. And if I got 2 parallel forces in opposite direction but they're equal, so 3 Newton, 1 to the left, 1 to the right, the resultant force is 0. So this box will just be as it is. There's no need to draw another arrow. Okay? So parallel forces are easy because they act along the same along the same axis. But the main problem will always come when you have forces acting like this. Okay, so not parallel and they are at an angle. So how to go about doing a question like this? Okay, how do I find the resultant force if the forces are not equal and there's an angle between them? Okay, they are at an angle. So this is what I call typically for my classes. Okay, they say in this textbook they say there are 2 methods of adding non-parallel. There's a parallelogram method. There's a tip to tail method. Okay, what I advocate is actually the parallelogram method. Okay, it's a lot easier to draw in my opinion. Okay, it's a lot clearer if you ask me. Okay, so now, so the steps are all written here, so I'm just going to go through step by step. Okay, first up, choose an appropriate scale. Okay, so once again, you always must start off as a step 1, choose the scale. Only when your scale is done properly, okay, when you've chosen a right scale or a scale that you want to use, then you can start to draw the vector diagram. So in this case here, the scale chosen is 1 cm is to 1 Newton. So the person drew 5 Newton here, 3 Newton here. How long actually is this 5 Newton and 3 Newton? Because of the scale 1 cm is to 1 Newton, this is actually a 5 cm line. This is actually a 3 cm line. Okay? Now, because you know this is 40, this is 20. So what you can do is you can just draw a 60 degrees between the two. So I will draw 5 Newton, which is a 5 cm line, with one arrow over here. Then I'll measure 60 degrees. Then I'll draw another line. That's 3 cm long. So like this, this is 5 cm. This is 5 Newton, which is 5 cm because of the scale. This is 3 Newton, which is 3 cm because of the scale. And then it is the difference between them is actually 60 degrees. So once I've drawn this, okay, the next part is actually to complete the parallelogram, step 2. Now, if you read the steps here, complete the parallelogram by adding the dotted line AC and BC, which are parallel to OB and OA respectively. How do you draw these parallel lines? Okay, the trick that I always teach my students is this. If the angle here is 60, to draw the next line over here, what you need to do is this angle will be 180 minus the central angle here, which is 60. So this is going to be 120 degrees. So I measure 120, then I draw a dotted line. Same thing, the angle that's going to be over here will actually also be 180 minus the central angle over here, which is 60. So I'm also going to get 120. So I'll measure 120 over here, then I'll draw a dotted line. Right, so you can see here is my freehand parallelogram, which you're going to have something like this. Then the resultant force is always from the starting point to the ending point. This is the resultant force. What is the magnitude of the resultant force is actually the length. So if my scale is 1 cm is to 1 Newton, then when I measure here, it is 7 cm, so it will be 7 Newton. Okay? The angle, okay, it can be this angle or it can be this angle. Any one of them will do. Okay, so this is just a quick revision on how to go about drawing the vector diagram itself. Okay, you would have worksheets, you would have worksheets on this, you would have some practices on it. Okay, so do go back and revise on this. Because O-level it does come out, and when it comes out it's about 3 marks sometimes. So do make sure you know how to draw it, because it's actually quite easy to draw. It's just a few steps that you need to follow. Okay. Now, I won't go through this tip to tail method, because when you need to draw vector diagram, you're not expected to learn how to draw parallel and tip to tail method. Whenever they ask you to draw vector diagram, you just need to use either one of these methods to draw. So my focus has always been on the parallelogram method, okay, and hence I will just cover the parallelogram method. Okay, this one can be quite confusing at times. That's why I don't want to go about using this. Okay, so what's the key concept here? Why are we drawing this vector diagram? Why are we using the parallelogram method? The key idea, so put one star here, key idea, we are trying to add two forces, okay, which are acting in different direction. Right, so actually you use the parallelogram method, you use the vector diagram, it's really to add two forces who are acting in different direction. When I put different direction, I mean that they are at an angle, some sort of a weird angle that you just can't add up the forces, like just take 5 plus 3, this kind of stuff. Okay, you need to draw it out to determine the resultant force. Okay, so there are some book examples here, you can go through them. Okay, so this is the parallelogram method. So do take a look through it. Tip to tail, you can try it out, but I won't advocate it. Okay, so just some key idea for the vector diagram part. Really is what you're trying to learn is how to add 2 or more vectors, okay, or 2 or more forces acting on a body. Okay, so if it is parallel forces, okay, it's quite a simple, either you add them up if they're in the same direction, or you subtract them if they're in different direction. But if they are non-parallel, that is where you will need to draw using a parallelogram method. Okay, so this is for 3.2. By the trend so far, you realize that vectors do come out here and there, but it's not very consistent. So when will it come out again? You'll never know. But it's quite good marks. It's about 3 marks typically, okay, for the exam. So learn to draw them. It's not very, very difficult actually. Okay. This will be a good practice. So you can try using question 2 okay, to go and draw the vector diagram itself. Okay, so I won't go through that anymore. Now let's go on to 3.3, forces and motion. Now, in this 3.3, what you're going to learn is that you're going to learn how to apply Newton's law of motion. There are total 3 laws: Newton's first law, second law, and third law. Okay, we'll go through it later. But we're going to look at how each of these laws is able to help us to describe how a force can change the motion of a body. Okay, and the law itself will also help us to describe the effects of balanced forces and unbalanced forces on the body. And the last one, out of all this, you're going to learn how to apply your famous formula, F equals to ma. Okay, but do take note, look at the F here. This F is not any other force. It's not just a force. It's actually the resultant force. So do take note, whenever you're applying F equals to ma, you're always using the resultant force. Okay, you're always using the resultant force. So that's what we're going to cover in 3.3. So let's start first on the effects. So what are the effects of a force? You can either cause a body at rest to move. So a stationary object, once you exert a force, it starts moving. So this one is to start moving. Okay? A moving object increases its speed. So for example, a car moving at 10 meters per second, you apply a driving force, it becomes 20 meters per second. So there's an increase in speed. So a force can cause an increase in speed. And of course, if I can increase it in speed, a force can also cause a decrease in speed. Just like when you press the brakes on the car will slow down. And last one, it can cause a moving body to change the object. I think this one, racket sports, is a very clear-cut one. Okay. Now, in actual fact, when you talk about changing direction, actually what happened is you're actually slowing the object down. Okay. There's a decrease in speed. Then the object will come to a stop. Then you cause it to speed up again. So actually, whenever you're changing the direction of an object, these are the 3 motion that typically happens. Okay, typically whenever you're talking about like a tennis ball or badminton shuttlecock kind of thing, right, you will see this happening when there's a change in direction normally. Okay. Now, so let's go on to the rest of this part here. Okay. I think this part here, there's a little bit. Okay, a little bit of things that you need to know. Okay, now what is the thing that people tend to forget or tend to get confused about? Okay, that is actually inside here. So when a force is applied on an object, it can cause a change in speed and or direction, which is a change in velocity. I think this one we all understand. And because there's a change in velocity, there's a change in acceleration. Because what we learn is that, remember, in chapter 2, acceleration equals to change in velocity over change in time. So if there's a change in velocity, that means there must be a change in acceleration. Okay, so that's what we cover in chapter 2. Okay, so in order for us to change the velocity, we need to apply a force. So force leads to acceleration, and acceleration leads to change in velocity. Okay, so I say again, a force leads to a change in acceleration, and acceleration leads to a change in velocity. So this is how force links to velocity. Okay, now, so this is the big question here. Does this mean that there's no force acting on an object when the acceleration is 0? Okay, I repeat again. Does it mean that if there's no acceleration, which means that there's no change in velocity, does it mean that there's no force? The answer is no lah. Okay, 0 acceleration just means that the object is stationary or moving at constant velocity. Okay, even though acceleration is 0, it doesn't mean that there's no forces. It just means that the resultant forces is 0. So for example, if I give you an example like this, a box, stationary, exert 5 Newton here, exert 5 Newton here. The resultant force is 0. And because the resultant force is 0, okay, the object will not move at all. So you can see here in this case, even though acceleration is 0, okay, so 0 Newton, 0 resultant force means that acceleration will also be equal to 0 meter per second square. Resultant force 0, acceleration is 0. Right? But in this case here, do you realize that there are 2 forces acting on it? As such, what it means is that even though acceleration is 0, it doesn't mean that there's no forces. It only implies that the resultant force is 0. Okay, we'll see more examples of this later, so let's go on. Now, balance forces and Newton's first law. So if the resultant force acting on an object is 0, we say that the forces acting on an object are balanced. So balance force. What is the effect of a balance force? It actually tells you that acceleration equals to 0 meter per second square. So I need you to know this. Balance force means that acceleration is 0 meter per second. Why is acceleration equals to 0 meter per second? Because my resultant force is 0 Newton. So one leads to the other. So balance force tells you resultant force is 0. Resultant force is 0 tells you acceleration is 0. Okay? So this is something that you need to know, and you will realize that it always like to come out in your tests and exams also. So you must be able to apply them. Okay, so the two examples here, they say that the weight of the book is acting downwards. The table exerts a normal reaction force upwards. These two forces are equal. Okay, as such, resultant force is 0, and hence it remains stationary because acceleration is 0. Okay, so resultant force 0, acceleration 0, book remains stationary. Now, resultant force is 0 also tells you that there's no acceleration. So if an object is moving at a constant velocity at the start, constant velocity, if I got two forces acting equal, so I push the book forward, but there's a friction force acting backwards, the pushing force and the friction force is the same amount. Okay, they're equal. What we realize is that the resultant force is 0. And if the resultant force is 0, the acceleration will also be 0. If the acceleration is 0, means that the book will continue to move at a constant velocity. Why? Because if acceleration is 0, there's no change in velocity. Okay, so key idea here, key idea. What's the key idea here? It is that when forces are balanced, okay, this will mean that the resultant force is 0. When resultant force is 0, it means that the acceleration is 0. So yeah, the acceleration is 0. And when the acceleration is 0, there can be two consequences. It's either the object remains stationary, or the object continue moving at constant velocity. Okay, so this concept here you need to know. Okay, this is actually an implication of Newton's first law. It says that every object will continue in a state of rest or uniform motion, okay, unless a resultant force acts on it. Okay, so actually Newton's first law sort of like explain this whole part over here. Okay, so now if you look at the Newton's first law, it says unless a resultant force acts on it. So the thing here is, if there's no resultant force, this is what's going to happen. Okay, this is what's going to happen. But if there's a resultant force, then the question is what happens next? So this is when Newton's second law comes into the picture, when there is an unbalanced force. So when there's an unbalanced force, you know that the resultant obviously is not 0. So resultant force is present. Once you have unbalance, resultant force is present. If you have a resultant force, it means that acceleration occurs. Okay? And when acceleration occurs, the object can speed up, the object can slow down. When will it speed up? When will it slow down? Okay, for it to speed up, the resultant force is in the direction of movement. So for example, my resultant force is towards the right, and the object is actually moving towards the right, it will speed up. When will it slow down? It's when the resultant force is in the opposite direction of the movement. Okay? So example, when the object is moving towards the right, but my resultant force is towards the left, or a different direction, that's when the object will slow down. Okay, so this is the implication here. Okay, these are the effects that will take place when there's an unbalanced force. So okay, you can read through examples here, I won't go into it. Okay, but one of the key effects here, as you read out all this, you realize, Newton's second law, there's this part here. The product of the mass and acceleration gives the resultant force. This is actually the idea of F equals to ma. The formula that you always use, F equals to ma, actually stems or comes from the Newton's second law. Okay, it's telling you that to find the resultant force, okay, you take the mass multiplied by the acceleration. F equals to ma. Take note, the mass must be in kg. The acceleration is in meter per second square. The resultant force is in Newton. Okay? Okay? So, this formula, most people always get it wrong because they forget that the F is actually talking about the resultant force. So you cannot just anyhow insert an F whenever you want to use this formula. You must always make sure that the force you are finding is the resultant force. Okay? Or the force that you are using is the resultant force. Okay? So every time when you do a force question, whenever you're going to apply F equals to ma, the first question you must always ask yourself is the F that I'm using here the resultant force? Okay? If yes, then continue. If it is not, then you need to find out how can you get the resultant force. Okay? So that's this part over here. Okay, so many examples. I think you have done F equals to ma enough in your Sec 2 life already, and then Sec 3 also, I think you've done it quite a fair bit already, especially in your exams and stuff. So I won't go through that one too much. I think I really want to go through a bit more is actually on the Newton's third law. Newton's third law is actually a very interesting one that we seldom talk about it, and actually we seldom we seldom talk about it, we seldom actually apply it in our question. Okay, but this is still quite an important concept. Now, so Newton's third law states that if body A exerts a force on body B, then body B will exert an equal and opposite force on body A. So example, the leg exert a force on the wall. So leg exert on the wall. What has happened is that because the leg exert a force on the wall will exert an equal but opposite direction force on the boy, on the feet of the boy. Okay, I give another example. For example, this is the person's face. Okay, this is the person's face. Okay, my very nice drawing here. Okay, happy man, happy boy. Okay, I got my hand over here. Oops, let me redraw this hand again. Okay, nice hand here. That goes and slap him. Okay, this is a classic example I like to give my students. Now, when you take your hand to slap a boy or slap a person, what you realize that when you slap the person's face feels pain. But at the same time, your hand also feels pain. Why is it so? It's because when your hand exerts a force on the face of the person's face will also exert a force back on your hand. That's why your hand also feels pain as you whack the person. But it need not be slapped. Sometimes it need not slap the face. Sometimes by slapping on the back of a person, okay, you also feel the effect on your hand. So key idea here, Newton's third law actually always is around us all the time. Okay? So all these examples over here. Okay, I won't go through most of the things here. I think really the key concept I want to go through is the key ideas here. So you can see forces balanced, resultant force is 0. Resultant force is 0, acceleration is 0. As such, object at rest will remain at rest. Object in motion will remain in motion at a constant velocity. So you must be able to write out this sequence. Right? You must be able to write out this sequence. If it's an unbalanced force, what's going to happen? If it's unbalanced, resultant force is not zero. If resultant force is not zero, means acceleration is not zero. Means that there's acceleration. So the object will either start moving or the object will change its velocity. Right? You must be able to say in this sequence also. So whenever you see explanation question revolving force and asking you to talk about the motion, this is actually what's expected of you. I say again, this is actually what's expected of you. You either need to say A or you need to say B. Right? Do flip through your TYS, you'll realize that these questions are quite common in kinematics and in forces. Right? Do learn how to explain them using this sequence. Okay, now next one, formula F equals to MA, that's what we covered. This one is just a further elaboration of point number 3. Last one is Newton's third law. It states that for every action, there's an equal and opposite reaction. So another classic example, I got a book placed on the table. It is a book placed on the table. Because the book has weight. Okay, the book has a weight. So the book is exerting a downward force on the table. By applying Newton's third law, okay, you realize that the table will exert an equal and opposite force on the book. Right? This is actually applying Newton's third law. And this orange arrow that I'm drawing here is actually a normal reaction force. You realize this is the surface. You see this perpendicular to the surface. This was what we have gone through at the very start at unit 3.1. I want to go through a little bit more about this normal reaction force thing. Okay, I give another example. I have a car. The 2 wheels are here. Okay, it is stationary. What's going to happen is that the car exerts a downward force. Okay, sorry, let me draw my wheel properly. Okay, the car exerts a downward force, which is actually the weight. Okay, and because of the weight, the car exerts a force on the ground. So what's going to happen is that because the car exerts a force on the ground, by applying Newton's third law, there must be a force that's acting from the ground on the car, acting from the ground to the car. Now the question is, where is the ground in contact with the car? It's actually at this point here and this point here. So at these 2 points, there's an upward force. This 2 upward force is actually what we call the normal reaction force. Normal reaction force. This normal reaction force, do take note, is always perpendicular to the surface. Okay, that's the first thing. And it's a reaction. It is a reaction force to an existing force. So in this case, the weight of the book, normal reaction force, is the reaction. So this normal reaction force is actually a reaction force for the weight here. This 2 upward force over here is actually a normal reaction force for the weight of the car over here. Okay, and you realize it's always at the point of contact. At the point of contact over here. Okay. Quite common question that I like to ask you to draw is the free body diagram. So do take note of how to go about doing this. Okay. That's how you're applying actually the Newton's third law. Okay, next one. 3.4, friction and its effect. So do take note, friction is the contact force that opposes or tend to oppose motion. Okay, so friction opposes motion between surface. This is a result of irregularity on the surface here. Okay, so because there's all these jagged edges, this is when you see in a microscope or even smaller at the particle level, you realize that they will like sort of hold on to each other. That's where the friction comes in. Okay, now there are many effects of friction, there's positive and there's negative. So actually we can walk is because of friction. Without friction, just imagine ice skating. You can't really move forward. It's difficult and you will just keep slipping. Okay. Moving vehicles are able to slow down when needed. Okay, so be it. Negative effects, make things less efficient, make things suffer wear and tear. But I guess really the key idea behind friction that most people, or like most question people tend to get wrong, is actually this. Okay, it's really about the wheel. Okay, it's really about the wheel. So this is the ground, this is the wheel. If my wheel is moving in this direction, so turning is this direction. So this is the turning motion. Right? If this is the turning motion, or this is the turning motion, then my question is, at this particular point here, what is the direction in which the friction is acting? So this is the common question that people tend to get wrong. In the TOS, you will see this question also. So key idea, ask yourself, at this particular point, okay, let me use a different color. At this particular point, okay, the wheel is moving in each direction. So imagine you see a turning motion like this. At this particular point, actually the wheel is going in this direction. Can you see? It's towards the left. The wheel is moving towards the left. See here, so because turning motion, right? At this particular point, the wheel is actually turning towards the left. So the motion is towards the left. What do we say about friction? Friction is a contact force that opposes motion. So if my motion is going towards the left, my friction must act towards the right. So this is the direction of my friction. It may sound counterintuitive, because imagine if the wheel is turning like that and my car is moving forward. I thought friction will actually be like going backwards. So this is the part where you must really analyze the motion. Ask yourself, how is the wheel moving? And then from how the wheel is moving, you determine the friction. So this kind of question, you must take note, you must learn how to do it. Okay? Because this is the trickier kind of question. The typical box question is easy lah. Okay? I think you have seen me draw it once, but I'm going to draw it again. If the box is moving forward in this direction, so this is the forward motion. So if the box is moving forward, obviously friction must be going backwards. And friction is a contact force, right? So contact is over here. So therefore, my friction is actually this direction. Friction. Okay, along the surface, opposing the motion. So situations like this are easy, but when you go to a circular motion where the thing is turning, that's where it gets a bit more complicated. Okay, so friction wise, do take note of this particular example. Okay, the rest of it, I think you can read out on your own. How you can reduce friction using ball bearing, how can you use lubricant or polished surfaces, use air cushion. Okay, this is really just to let you appreciate the things around us, how we are trying to reduce friction in the things around us. Okay, how frictions can be enhanced, okay, such as treads on the wheels to increase friction so that it can move better. Parachute, so that we have higher air resistance, so that we can slow down faster. Okay, last one, chalk on the rock climbers, so that they can climb the surfaces better. So all this is really more of the appreciation part of it. Okay, but so far I haven't really seen all this coming out for the exams. They don't really test you on this. Okay, they don't test you like, oh, what you can use to improve, what you can use to reduce. Even if they ask, most of you have the common sense to know what to write. So I doubt these are things that you want to waste time to memorize. So just read through, have a sense of appreciation on how you can increase the positive effect or decrease the negative effect. So key idea, friction, contact force, opposes or tend to oppose motion. Okay, there are both positive and negative effect, so get to understand them a bit more. Okay, last one, 3.5. Okay, last one for forces itself. Free body diagrams. So actually all this drawing that I've been drawing, this wheel thingy, this box thingy, okay, this car thingy, this book thingy, all these are actually the free body diagram. So so along the way I've actually been seeing free body diagrams. So free body diagrams, actually what are they? right? They are sort of like simple block diagrams that represents forces acting on an individual object. Alright, so I say again, what are free body diagrams? They are simple block diagrams to represent forces acting on an individual object. So example, the bird. You realize the bird, there's an upward lift, so I can draw an arrow from the bird. Right, the air resistance. Downwards, the weight of the force of the bird. Right towards the left is I saw when I flap the wings, it's also going forward. There's a thrust by the wings. So this is an example of a free body diagram. Next one, an apple hanging on the tree. So there's the weight acting downwards. But why is it still staying there? Because the branch is having a tension force, okay, acting upwards. That's why these are the two forces acting on the apple. So this itself is a free body diagram. This itself a free body diagram. Next one, an apple falling down. So once again, the weight acting downwards, the air resistance acting upwards. So this itself is also a free body diagram. Another one, weight of the apple acting downwards, the normal reaction force by the ground acting upwards. This itself is also another free body diagram. So many free body diagram examples over here. Okay, so learn how to interpret them, learn how to draw them if necessary on questions. Okay, so all these examples, do go through them, read through. They're actually quite meaningful. It helps you understand how to apply the various principles, okay, for forces. Now, last one, 3.6, pressure. So we have covered this, but I think really just to reiterate a little bit of stuff using the sneakers and high heel example. So I think the interesting thing is, if you read the question, right, if a woman wears a high heel walking on muddy ground, her high heel will sink. She can avoid this by wearing sneakers. Why? Well, how come she can avoid this by wearing sneakers? Look at this. Look at the way how they explain this. First thing they say, whether they wear high heel or sneakers, her shoe exert the same downward force on the ground because the force is due to her weight. So her weight is the downward force that is acting on the ground. So it's constant. It's a constant force because her weight, it has always been her weight, it's the constant force. But why is it that one sink and the other doesn't sink? So it's not really about, so the sinking into ground, okay, is actually about pressure. It's not really totally about the force. Okay, so when the person wears high heels, her weight acts on a smaller area. When she wears sneakers, the area is bigger. So therefore, because of the weight acting on a smaller area is higher pressure. If it is a bigger area, it is smaller pressure. Okay, so you can see the conclusion here. The pressure exerted by the high heel is greater than that by the sneakers. The pressure exerted by the high heel is greater than that of the sneakers. Okay, so pressure is the one that causes the object, whether it's going to sink in the ground or not. So what is it defined as? Is a force acting per unit area. So whenever you see the word per, this is the concept of divide. So force acting per unit area. So pressure equals to force over area. Do take note of the units. The pressure, the units is actually in Pascal, PA. Force must be in Newton. Area should be in meter square. Okay. Now, question some people are asked is, is it possible to use cm square or not? So if I take pressure, okay, force divided by area. In my area here, I use cm square. The force here, I use Newton. So what's going to happen here is that the unit for my pressure will become Newton per cm square. You will sometimes see this unit around. So don't be too shocked. Pressure need not always be in Pascal. Pascal is the SI unit. Okay? But it is possible for pressure to be Newton per cm square because Newton is still force, cm square is still area. It's just that you're not using the SI unit. Okay, so please take note of this. Okay, so Some of the qualitative questions that can come out, okay, is a plastic bag like this, by adding a cloth, how does it help? Okay, so I want to explain this one a little bit more with the padding part. So this one, the fingers hurt because of the high pressure experienced by the hand, by the fingers. Now, how does the padding help? So actually the padding doesn't change the force. The padding actually increase the area. So since pressure equals to force over area, force is constant because this is the weight of the bag. But area increase, comma, therefore pressure exerted on the fingers is lesser. So if there's lesser pressure exerted on a finger by the plastic bag, definitely it wouldn't hurt that much. Right? So this is a kind of qualitative response that you need to learn how to explain. So it's not just every time I can calculate can already. You must be able to answer the things qualitatively. So you realize for today's lesson, right, I focus quite a fair bit on the qualitative part. One is this kind of question for pressure. Okay. If I were to scroll up a little bit more, you realize I also emphasize a little bit on this. This is actually how you qualitatively explain things. Okay, that means using words to explain. Most of you can calculate because formulas just apply like math. But explanation has always been an issue because your focus has always been on the calculation part. So learn to apply this kind of flow chart to lead you in your explanation. Okay? So going right to pressure, yes, so explaining this. And you realize that, oh, you mean that's the end, right? Yeah, after all this calculation, after pressure, all this, and you realize, ta-da, we are at the end of the chapter itself. Forces, the chapter actually really isn't much. There isn't too much about it. If you are able to use F equals to MA, you are able to use pressure equals to force over area, you realize that, most of the calculation questions I can do already. The only kind of question you will struggle with is really the explanation type. Okay, which then you must apply this, you must apply this, or you must apply this. Okay, so the application for these questions are really critical. And how to improve on explanations, first thing, you need to know your concepts well. Okay, just like how I mentioned, this F is not any ordinary F, it's resultant force. You are unable to get this kind of simple concept right, you're going to have issues explaining it. What else do I need to know? Okay, you need to know this force here. Whenever you're looking at pressure question, this force, what is the force that they're referring to? This area, what is the area that I'm referring to? Okay, otherwise, how do you explain it? So many of these questions it's not just about, I know the formula I can do. It's always about understanding what each of these terms mean. What each of these terms mean. So if you don't know what they means, go back and revise a little bit more. Now, then of course the next question is, how come our worksheet don't really talk so much about the Newton's first law, second law, and third law? Okay, a lot of the things we are doing is applying it already. So you realize first law leads to the balance forces. Second law generally is to calculate for the unbalanced forces. So you realize these two we always use one. Okay, only the Newton's third law part is the one that we seldom use. But in actual fact, you realize actually you got applied before. This one, typically you will realize we apply it to the normal reaction force. Okay, we apply this in the terms of a normal reaction force. And when do we draw normal reaction force? When we look at free body diagrams. Right, free body diagrams. So this is the part of forces here. Most of it you should be quite familiar with it already because you have seen it from Sec 2, Sec 3 until now. Okay, key idea, practice it, work on the qualitative part, the explanation type of questions. Okay, learn to explain them in a sequence, in a good flow. Okay, So that's for forces here. I don't have anything much for you already. So that's all for today. Key idea: practice, 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 practice. Okay, that's all from me. So that's all for today. Yep. Bye, everybody.